Normally as well, I boast about my location, but I think Crete compares. And it's also very nice to me because my very first summer school was in Crete back in 1993 on quantum optics. So this is my second work meeting in Crete, so there's been a long gap in between the two. I'm going to talk about multi-thin fibers and some of their applications with regards to using them in atom systems, and also some of the plans that we have in my research group in this context. You've already heard a number of people presenting ultra-thin fibers as possibly a system for 1D networks, but you actually haven't had a talk on ultra-thin fibers. So a lot of my talk is going to focus on the fibers themselves. Then I'm going to show some of the results that we got in the last year with them, and then some of the plans, sort of ambitious plans that we have for these systems. Just first of all, for those who don't know where Okinawa is, this is a map of China. You know what Japan you know, maybe you know Taipei, and then you just go a bit south from Tokyo, so a 3-hour flight. You find a long chain of islands. This is the Ryukyus chain, or otherwise known as the Okinawa Islands. And Okinawa is the largest island of the Okinawa Islands, and we're based in a fishing village on Okinawa Island, which is also very popular for honeymoon tourism. So similar colours of the sea as what we have today here in Crete. This is a vision of our university, so this is just very early part of the university, when just 1 or 2 labs were built. We're in a constant expansion phase, and here's the sea, as you can see, similar to what we're seeing outside today. So since this is a working group meeting, rather than just simply a conference talk, I figure I haven't got to many of the working group meetings before, so let me just very briefly introduce what we do within the group. So I'm actually called a unit, so I run 3 groups. I first of all have the Quantum Technologies group, and this is where we use nanofibers within cold atomic systems, sometimes within atomic vapor, in order to look at novel trapping and optical manipulation of atoms. We look at a lot of nonlinear optics work with this. The other section I work in is optical cavity and sensing group. Here we have whispering gallium multiresonators. Again, we've had a few talks in relation to whispering gallium multiresonators here. Particularly we work with microspheres and microbubbles. Again, for nonlinear optics, frequency comb generation, we've just started working on some rubidium spectroscopy with these systems. And then the final one is quite different. It's a nanobio-optics group, and here I have projects on optical trappings, optical tweezers, plasmonics, looking sort of at ultra-electromomentum transfer through nanoapertures. And then the very final project, you may be wondering why I have a mouse here, we also do some neuronal imaging research. So this is somehow the ethos of OIST is that we have no constraints and we can do research in whatever area we're interested in, even if we have no background in it. So hence the mouse research that I'm also doing. Just to point out again, because working group meeting, short-term scientific missions are allowed to come into Japan. We're not allowed to go out, but you can send your students to us within Japan, and we're very happy to welcome them. We have nice, reasonable accommodation, and some of you interested in coming and working on any of these projects, please let us know. So now to the talk. So brief introduction to optical nanofibers, that's just some of the work that we've done recently. So optical nanofibers, said you've had a number of talks. Obviously optical nanofibers are not simply nanofibers. The advantage of optical nanofibers is that they're fabricated from standard optical fiber, so therefore they're very easy to integrate into an experimental setup. So you take a standard optical fiber and you heat it and stretch it by whatever means you choose. Normally in the atom community, we use flame, ideally hydrogen oxygen if people are allowed hydrogen in their labs. And that gives you a very clean fiber, or a very clean nanofiber at the end, which is extremely important for any of the atomic work. So if you start work, try to work with a fiber which is in any way contaminated, you can't integrate these into atomic systems. The crucial area is the waste. One of the ways we get very good light propagation, so if we put light in here, we effectively want 100% of that light to propagate through the fiber. This is dictated by this transition region here. We can choose the transition region. It could be an exponential transition, which would be sort of typical. But if we want to put in higher order modes for these nanofibers, for example, we work with ultra-micro momentum modes, then we need to choose a transition which is not exponential, and typically it's a number of linear steps within this transition. Then at the waist, you obviously will have an evanescent field because your light mode is confined, and in this evanescent field, then you can interact with whatever you put in the environment. And then the light comes back into the transition, and we always assume that these transitions are symmetric. So just why are these versatile and why are they good? Look, I think mentioned a couple of reasons already, so did Peter Sala, and a few others that Rich also mentioned. So these are very good for low light levels. This is one thing that we find we can really work with a few atom system, really working very, very efficient detecting low light levels. The other thing that we have then is nonlinear optics. We could do not because of the confinement of the modes into a very small mode region here, we end up with extremely high intensities for very, very low powers. So a lot of the conditions that you can normally have with nonlinear optics are removed, i.e. buy a big, expensive, high-powered laser. So we can remove that condition, and we can work with picowatts of power. And then this is one of the advantages that Peter Sala mentioned. So this is working with spin-off coupling. Okay, so you bring a system close to your fiber, and you can play with the spin of the light, and then couple that into the system that you're working with. So these nanofibers, how do they compare to a normal optical fiber? Well, this is quite technical. A normal optical fiber, the light is propagating based on the way of the refractive index difference between the core and the cladding. And normally in a single mode fiber, which is made from silica, this would be a very small refractive index difference. So the sort of refractive index difference we're talking about is of this order. And this is designed so that the light is confined within the core. So here we're just looking at the light field in the grid here is indicating the boundary of the fiber. However, in a nanofiber, what you're doing is that when you heat it, you're effectively removing the core from the equation. And the cladding material starts acting as a core, and whatever is in your environment starts acting as the cladding. So if your environment is a vacuum, you change this refractive index quite dramatically, and now you have the cladding, and the environment is now cladding, which is a refractive index of 1. And in this case, you end up with this evanescent field, and this is the evanescent region of interest. So it's this evanescent field that can interact with your particles. The other condition, which I don't think is mentioned here today, is the cruciality of polarization in nanofibers. So nanofibers are not made for polarization maintaining fiber. Okay, so any polarization you put into the system will change as it's propagating. If we look at high polarization, you get typically two lobes either side of the fiber, and these are what most atom traps are based on. Alternatively, you can have sigma polarization, and then you would have cylindrically symmetric evanescent field around the fiber. However, with regards to atom traps, these are very hard to load. So therefore, it's not the case that people are working with this because it's easier to load for a trapping system, but also because people aren't able to necessarily maintain the sigma polarization right down through the waist. And just to point out, there are quite a lot of groups working on atoms and fibers. I think a lot of people aren't aware of how many groups there are, and I've listed some of them here. So the Julien Laurent, Paris, Watson, Roscoe, and JQI, Atemi, who was also with Watson and Roscoe. There's Bart Aya, there's Eugene Ponce, Arno Bauschenbeutel, Mark Buderland in New Zealand, Kozo Haskell, who was really one of the first people to work in this field, and then Mark Sadgrove, who came out with his group. And this list is not exhaustive. However, a lot of these people haven't yet published, so maybe about 5 groups have already published on the topic. But there are a number, sort of an exponentially increasing number of groups because offspring are now being created from these groups. So here's a bad fiber. Okay, you're probably wondering what these fibers look like. So we can't show you a good fiber because if it's good, you're not going to have any losses, which means that you're not going to see any of the light passing through the fiber. So we can only show you bad fibers. So if you make a fiber, typically this is what people in the whispering gallery mode community will make, okay? It's a bad fiber. They don't care, they can just put more power in, it's in air with no conditions about heating the fiber. These are just dust particles, we can remove those dust particles. Here's another type of interesting fiber that can be created. This is not using a flame, so this is using a heat source, a micro oven, and here you can see some beating effect due to some standing wave configuration that we've generated within the fiber. So effectively we can create some type of grating within the fiber during the fabrication process. Now, the crucial thing in all of these fibers, the nanofibers, and a normal single mode, or what do we mean by being multimode? Well, this is all dictated by one single number, which is called the V number. The V number is related to the radius of the fiber, the wavelength I'm using, and the refractive index differences. So here's a typical plot that some of you will be familiar with. So this shows the V number as a function of the normalized propagation constant, and these are approximate modes that you can have propagated in a fiber. Okay? And if we say we want a single mode fiber, it means the V number should be less than 2.4. Okay, so no matter what wavelength, no matter what size fiber, the magic number of 2.4 comes out. So here's the V number indicating it's less than 2.4, so anything to the left of this diagram, wherever I have a mode present, that will propagate as a single mode. Wherever I have to the right of the system, these modes will not propagate. Okay, so in this case, if I have a fiber at this value, I'll only get single mode propagation of the LP01. If I have this value, I would have mode propagation across of the LP01 and across of the LP11 family. So now I would have multi-mode fiber, or in this case it's a 2-mode fiber. So it's a pretty simple process. So if I want to design a fiber, I'll either design it so that it's single mode for a specific wavelength. That means it would be multi-mode for other wavelengths. And this is one of the really crucial parts in these atom experiments. So in an optical nanofiber, it's a little bit more complicated, of course. We can't make approximations, so we have to look at the true solutions. And instead of these LP modes, we end up with the HE, TE, TM, and so on. And then, of course, some of these carry interesting features, such as the orbital angle that I was mentioning. So again, HE11 is our fundamental modes, effectively a Gaussian, TE, TM, HE, various profiles, and then ones that we will only ever excite in our fibers. So we try to avoid exciting any modes beyond this group here, so the LP11 group. These are what these modes look like. So effectively this is Gaussian, and then this has more like a donut bean shape. And the advantage of if we can exploit this sort of behavior in a nanofiber, or sometimes the fiber might be slightly bigger, so it might be just about a micron, means that we can, the evanescent field can usually extend a bit further into the environment. The evanescent field usually has more intensity, so there are some advantages to using these donut modes as opposed to the standard Gaussian. Now, also within atom fiber systems, there are a few different detection systems. So the very early work, which came out of my group, Kath's group, and Anna Hauschenberg's group, we all used this sort of detection. So we looked at the fluorescence of the atoms, but it was pretty limited in what we could do. We could only do sort of characterization of moss and so on. Then pretty quickly, everyone started to put the lasers through the fibers once we figured out how to get fibers that don't break as soon as you put some light through them, beyond a few photons. So this is the most common sort of detection method used. But this is also quite common, where people have limitations on how much power you can put through your fiber, because this is a serious experimental limitation. Then people will sometimes use lasers perpendicular to the fiber and just look at the scattering from this laser into the fiber modes. So why do we use this as a quantum interface tool? Well, I think this is going to be pretty clear by some of the theory talks that we've had, and also Wahid mentioned about the fact that we can avoid this problem where we focus a laser beam. So we end up with a much longer interaction region between our atoms and our photons when we're using a fiber. So our waste region is typically maybe 5 millimeters up to 1 centimeter long, and also we have very efficient photon transfer. So the typical configurations that you can use, either you start off just a magneto-optical trap, and you deal with your magneto-optical trap. You can look at the nonlinear effects in this way. You can also look at some things like multiparticle entanglement. You can look at coherences of emissions and so on. And the other alternative that people look at is fiber-based dipole traps. So this is a system that was first proposed by Feng Kien, Victor Balakin, and Koza Hakuba back in 2004. They had a series of papers on using these fibers. And there they proposed this one example here is just a cesium in this paper from Eugene Cousins' group, that if you have a red standing wave going through your fiber, you create some nodes, and therefore antinodes, so the atoms can get trapped. And then this blue is just to prevent the atoms from sticking on the surface of the fiber. So that they both have different decay lengths, and their evanescent fields, which just moves the traps a couple of 100 nanometers away from the surface. So the first type of work that I'll report here, we're primarily looking at first type, but we're also looking at second type. So what we have done are typical nonlinear optics experiments, and these are all heading towards trying to do Rydberg formation next to nanofibers. So the first thing we looked at alphotron splittings. So alphotron splitting is in this type of configuration. start off with ground state and are cold atoms. We excite them using the first transition from 780 from 5s to 5p, and then 776 from 5p to 5d. We don't look at this, okay, we just simply don't have a detector, and we monitor the 420 nanometer light. So these experiments all light beams pass through the fiber. So we optimize it for the 780, 776, same, okay, not going to make a difference for our fiber. And then we collect it using the 420 nanometer light, and we also determine the efficiency of transfer of the 420. And this is what these experiments look like. The blue line represents the fiber, okay, again, you can't see it when it's actually in place. So just to mention again that the modes are really crucial. So here we're looking at a number of wavelengths and figure out which modes we're looking at. So we're looking at 420, it's single mode at just about 2.34, so it's still left of this magic number, 2.4. And for the 780, we're well into the single mode region, so it's 1.26. You have to avoid having a V number smaller than 1 because then your fiber is simply too lossy. So the sort of results that we got on the outlet splitting. So for the upper transition, we kept it at a fixed power of 0.5 nanowatts, and then we scanned the frequency. For the lower transition, we kept the frequency fixed, and we scanned the power. So here we're scanning the power for the lower transition from here downwards. Okay. And here you can see as we're increasing the power, you start seeing splitting due to the outlet splitting of the intermediate level. So then the plot, the curve, the theory curve is just more or less a fit using some density matrix models. We can also look at the separation as a function of the power in the 780, so in the lower transition, and we see a linear fit. And this is exactly what we'd expect in order to be able to determine the Raman frequencies associated with it. After the outlet splitting, we then changed the configuration slightly, so we decided to look at electromagnetic induced transparency, because this is crucial for detection, also for any slow light type experiments. We work with a ladder scheme in our EIT. So very same transitions as before. We have 780 here and 776 here. And then we just monitor the transmission through the fiber. And when we have EIT, we see the change in the transmission through the fiber. And of course, there are other EIT configurations which you'll be familiar with, like the V, and this meeting, most people have talked about the lambda configuration. So when you have EIT, so the blue curve here represents when this omega C is off, so this is absorption, so just imagine it's the inverse of transmission through my fiber. When this is being absorbed, I will have very low transmission through my fiber. When I turn on my coupling beam, I will end up with higher transmission through my fiber. Now our system, because it's in a ladder type configuration, and we also were detuned to the levels, we're actually looking at a broad spectrum of EIT. So this is the setup. It's a counter-propagating system, just cold atoms around the fiber, looking at two frequencies going in. We have a probe light, we have the blue here is just representing the 776, this is 780. And again, these are just transitions, and this is sort of what we observed, so that's actually what we observed. So this is just standard to a vapor cell, and then as you change the power, 0 from 0, you see no evidence of EIT, and just as you increase the power, you start to see some very small evidence of EIT in these two signals here. So said because this is a ladder configuration, because our atoms, our optical depth is quite low, the EIT signal is not this really sharp transition that you may expect. And at the same time, about four groups published within a month of each other on this sort of topic. This was using a vapor cell, nanofiber, and these were both using lambda configuration in cold atoms. So what we want to do is go towards Rydberg atoms. So from neutral atoms to Rydberg atoms, and why would we be interested in these? Well, they're highly excited neutral atoms, but they're not ionized, so we hope that they stay not ionized next to our dielectric surface. They also have a very large dipole moment, large polarizability, and a long lifetime. There are certain features of Rydberg atoms when you end up having these very excited states, the features that we can take advantage of. So here if we just consider a Rydberg atom, this is ground state, this is excitation to a Rydberg, so you can excite using this light beam omega, and then if we have two Rydberg atoms nearby each other within what we call the Rydberg blockade, so separated by a certain distance r, you'll see that as this distance r gets smaller, the energy levels are shifted due to a van der Waals interaction, which is related to orbital 6, and you can no longer excite a second Rydberg. So you can have ground state, one Rydberg, but the excitation of 2 Rydberg atoms is, the probability is almost essentially 0. So what we'd like to do is to study the formation of Rydberg atoms next to nanofibers, because it's not all clear. People are looking at Rydberg atoms next to larger surfaces at the sort of tens of microns region, but nobody's been in a position before to look at something a couple of 100 nanometers from a fiber. So this is one of the first things we want to do, is just study this formation. However, as it's expected that what we will maybe learn from this is Rydberg surface interaction problems and issues, and effectively nobody has an idea of what will happen at this range. So it's going to be pretty interesting to see what we will get out. So the experimental plan, just very, very basic scheme, just to keep it simple. We have our nanofiber starting off with a lot of atoms, so these are rubidium 87 atoms again, and we will just do our Rydberg excitation. So we need 780 nanometers and 480 nanometer light propagating, so it's an EIT type Rydberg excitations that we're going to do. We would move this 480 just near to the MOT, but not necessarily near the fiber, and then just gradually approach the 480 to the fiber to see at what point we can or cannot create Rydberg atoms. So in the best case, we can create the Rydberg atoms, and then we will see our characteristic EIT signal. And ideally, this is what we would like to do. So trapping atoms along the fiber, exploiting the chiral properties that we can get using the spin-off coupling. Doing all our light beams through the fiber in order to try to see we've got a lot of light beams, so for this we need to be able to use reasonable powers for our fibers, because each power will be accumulative, and we can get up to maybe 150, 160 milliwatts through the fiber, so we should be able to achieve the powers required. And in this case, then maybe be able to form Rydberg atoms. So each of these big blobs is indicating the Rydberg atom. They can't fly closer than the Rydberg blockade, possibly, again not known at this sort of scale. And then within each Rydberg blockade radius, you can end up with some of your neutral trapped atoms. And this can be used as some type of quantum logic gate. So what we're currently studying is this formation. And we also can look at some resonant energy transfer between 2 Rydberg atoms, and this is possibly something that we can learn again on this sort of scale that we're looking at. And one thing to note is why have I not aligned my Rydberg nicely compared to my atoms? Well, the Rydberg atoms can't be trapped in the same way that neutral atoms can be. There are some tricks in order to trap the Rydberg atoms, but this is very far down the line. So there's a lot more to learn before we start trying to trap Rydberg. So how do we do this change from our neutral atoms to Rydberg? Well, it's pretty easy. All we have to do, this was our original EIT scheme, and for Rydberg atoms, all we're going to do is instead of going from this excited state here, which is an n equals 5 excited state, we're going to go to some n, where n is higher than probably somewhere above 19, depending on which laser we have, so probably starting around n equals 23 or so. And otherwise we've got the very same configuration, and then we would just do the very same type of EIT measurements. So what modes will we have then? In this case, the fiber that we're using is slightly larger, it's 400 nanometers diameter. And again, looking at the different ones that we have, so lambda equals 480 nanometers. In this case, for this excitation, it's going to be a multimode fiber. So in other words, we'll be able to exploit some of the higher order mode properties. For 780, it's still a single mode fiber, and then for any of the other wavelengths, it's going to stay single mode. So to summarize, we're looking at this sort of scheme. We've already done alpha-atom splitting and EIT neutral atoms next to nanofibers. Now we're looking at formation of Rydberg next to them and exploring the effects of the surface on the Rydberg. We also have another scheme that we're looking at. So this is what we call our slotted tapered optical fiber. So this is we take a nanofiber and then we use some focused ion beam processing and we remove the middle region. And effectively what we're left with is 2 nanofibers with a gap in the middle. Here we have them fabricated. This is a model of atom trapping within these slotted regions. We can change the length of the slot. At the moment we've just modeled it for quite a long slot because we're testing it with nanoparticle trapping. But in principle we could put this down for about 1 micron slot regions. We're also going to look at this fibre has an ITO coating, a very thin ITO coating in some areas of it. So with work with rigor people, we're going to look at the influence here of rigor formation of vapor, so a hot system. It's easier to get rigor in a hot system than in a cold system. And we can move the rigor or the system around and try to see whether the ITO is having an influence on that formation, whether it improves it, reduces it. Again, because the layer is so thin, people aren't really sure where we'll end up. So these are the main open questions with regards to what we're working on. At the moment, we have other projects in cold atoms, but these are the two most relevant to this meeting. Here's the group. The people with the yellow circles around their heads are the cold atom people. Just 2 people left at the end of last year, so we've just been building up our new experiments. So Ravi has gone to CPT, and Bandana has gone to join Peter Ingrams in the USA. And I'd like to acknowledge that our theoretical support on this comes from the Quantum Systems Unit. So Anna Kien has now moved over to OIST and is working with us in order to model these systems. And finally, I would like to make an announcement. We've moved the deadline to the 12th of June. This is our annual summer school that we hold in Okinawa, and it involves both cold atoms, ultrafast, and usually solid state. So you can see, maybe you can read this, maybe not. But some of these names have been mentioned quite frequently during this workshop and during the conference. So maybe some of you are interested. So if you are interested, you need to sign up pretty quickly because that's going to close, because I shifted the deadline just so that I could mention it to a new community. And at that, I'd like to thank you.
Thank you very much for this talk. Any questions? Yes.
So how invasive is the fibre to the mold, just the cold atoms? Does it do local heating? Do you send atoms? Do you have like convection currents that form all sorts of?
So, if there's no light beam going through, if there's no on-resonant light beam going through the fibre, it's very non-invasive. As soon as you put a resonant light beam, so probe beam through, you have to really keep it very low powers. I mean, you can immediately see in the vicinity of the fibre, your atoms are no longer, at 100 micron or colder, they're up at 800 microkelvin. It's not microkelvin. So it's overall, with regards to its impact on the atom's rise time, life time, decay time, all of this, it isn't a problem. But the only problem that we've seen arising is if you're using a probe beam, you need to keep it well below any possible heating issues.
And if you use multicolours, can you do dark field seeking trapping so that you can trap actually away from one of the atoms?
I heard if you use multicolours, and I didn't hear the second part.
If you can do dark field trapping, so dark seeking atoms, so that you can stack your potential away from the fibre, so that you then have your atoms closer to the fibre but outside the intense field, so you don't heat as them.
How do I answer that? Well, in principle, this would be true, but you still need a way of detecting on everything. So that's usually then becomes the criteria. Can we detect what we're doing? I mean, the only detection method for any of this fibre work is through the light that's transmitted through the fibre. So if we're not having any light scattered either into the fibre or an absorption signal from a probe beam, then the detection methods are pretty lousy. Nobody has put imaging or anything built into these systems so far. So I don't know if that really answered your question, but I think sort of probably did.
I have a question related to if you have a fiber and then there are atomic dots and instead of photon, then the strong coupling will be around coupling when analysis comes from the fact that the second photon is in any case present. And now if you have regular atoms and double K, and how to show that this coupling comes from double K or from these parts.
So with regards to the Rydberg atoms, nobody is sure of anything with next to a nanofiber. So I mean, the very first thing will be, even as said, we have to do everything away from the nanofiber and see if we can couple in any light into the nanofiber from the excitation. But one thing is that A lot of this is not, so from a theoretical point of view, people always say, you know, you've got 100% coupling, you've got 30% coupling, whatever. In these experiments, you're lucky if you get 10% of the emissions coupled into the fibre. So there are tricks that you have to play to try to shift frequencies and so on in order to be able to separate them out. But to actually worry that far down the line to even form Rydberg is going to be a big challenge. Playing with coatings that won't affect the evanescent field and so on.
Could you say something about the effect of absorption of the atoms on glass in terms of aging, but also in terms of whether you have...
Yeah, so this is really different for the nanofibers compared to the normal dielectric surfaces. Nanofibers are cold atoms, so we don't have any absorption of rubidium on them. So if we take an image on an SEM from our cold atom system, it's still completely clean, even after a couple of years.
Why is that?
We don't know, and nobody knows, but it's just the case. And it's not just us, it's the same for any of the people who start off with the extremely clean fibers. So it might be something due to the fact that when we're working with these systems, they have to be extremely clean. One dust particle and you can't work with them. So I don't know whether we have managed to really mitigate some of the surface effects by keeping them so clean initially. If we put the nanofiber into a vapor system, then we get, and we image it later, then we certainly see rubidium put on the system. The other people there are also people doing these experiments with hollow core fibers. They can't really image whether they have absorption on the surface, internal surface of the hollow core fibers, but the cold atom people believe they don't. But it's hard for them to prove it, whereas we can at least image. But these fibers normally last years until you decide you want a new fiber. So once you have a fiber in the chamber, it's a PhD student's fiber, and then the next PhD student will normally want to break that fiber. So there's some different behavior at this level.
Just a curiosity, you show this aim of having this nice chain of the linear chain of atoms on top of your fiber. Then you said these words that you would like to use the current property of the spin-orbital coupling to obtain that. Can you say a little bit more about that?
So this is what Peter and Sullivan was talking about, where you play with chirality. So effectively, by having state selection of your atoms. So normally you have, I showed at the very beginning, that if I use a linear or quasi-linear trap or light field, I'll end up with two lines of atoms along the fiber, okay, one at either side. And then you can play with the state selection of these atoms by directly addressing them. Get rid of the lower line, effectively, and then you're left only with the upper line. And this is all due to playing with state and the polarization of the light that you're using.